And greetings, friends. Welcome to class number 2 of this 10th week. So, 2/3 through almost. We have PLC 10 for this week. That'll be Friday. And then homework 6 is posted. I'd suggest getting started on doing that. That's going to be due Tuesday. We'll have celebration number 2 on that same day. So, excuse me. So the format will be the same as in the first. It will be a day of no class, no Zoom class, and it'll just be available and open for the day. And same deal, you take your time, you sit down, you do it, you make sure everything's squared away, and you don't turn it in late. So after midnight, or if you're over your time limit, you just need to be real careful because there's a pretty good chance that those aren't going to get accepted. So please be aware of your time, all right? Other than that, basically the same deals. You have the open book, so it's open notes. And I'm just going to remind you that does not mean open things like ChatGPT. No. So no online resources, class notes, whatever you've done for this class homework wise, quizzes. Oh wait, it would have been quizzes, but whatever else there is going on. So the celebration itself will be from the end of the previous one, which we then began with ray optics at that point. So this will be starting with things like ray diagrams, mirrors, lenses, refraction, reflection, least time principle, things like that for the rays, okay? Total internal reflection, that's another one. The drawing of diagrams, especially when we've spent time developing them, I highly encourage that. So if you're thinking, what should I study? Start refreshing yourself on the ray diagrams and how refraction looks and what does total internal reflection look like and these types of things. After that, we moved into the wave optics. So things like the double slit experiment, the path length differences, how do we get phase change, phase differences between waves, glass blocks, right? Double slits, thin films, reflections, not to mention polarization, diffraction, single slit, the idea of drawing the path length difference in the double slit, looking at the single slit, all these types of things will come in here. We are going to go through diffraction gratings today. And that will also be a topic, diffraction gratings, as you see it on homework 6. So we're going to take care of that today. And that will also be a potential topic for celebration 2. All right, so a little bit of wording on that. I'm anticipating the same length, which means same number of problems, questions, things like that. And we'll go from there. All righty. So I wanted to show you a couple of patterns, a couple of diffraction patterns. So I'm just gonna take a minute here as running downstairs to get the laser set up so that I can show you this. And that means I'm just going to put that there. We've got that there. And so what I have here is a an apparatus in which I have single slits. And I also have the ability to look through apertures, which was something we discussed last time, as well as other patterns. So I'm not sure if it actually makes a difference if the lights are on or off. What do we have here? Okay. All right. Well, let's see here. What we'll do is this. Okay. Like that. Maybe if I do that. All right. So let me go kill the lights off. Alrighty, now, if I get you a little closer here, that means taking you around this way and bringing you here. Alright, so that, let's see here, bring that there, okay. So if I can show you this pattern here, let's see if I can zoom you up into that pattern. Well, it's still not the greatest. The camera is definitely washing, it's looking at the brightness of the middle and it's adjusting on that. So if I maybe just do that, you can see a little bit better the side fringes. So this is slit width, this is a slit of a certain width. And now what I'm going to do is I'm going to turn it around this way so I can see what I'm doing. There we go. Okay. So that's a slit of a fairly large width. And now when I go to a slightly smaller one, and then a slightly smaller one, and then a slightly smaller one. You see what happens to the size of the central maximum, right? The central maximum, now I have a really small slit. This is a very narrow slit. The central maximum is now this wide, okay? And the first minimum you can barely see, even I can barely see it. It's about, they're about there and there, okay? So the narrower the slit gets, the more the central maximum takes, the more of the pattern the central maximum takes, okay? So here's a slightly wider slit, slightly wider, slightly wider. And that one, like I said, you can't really see super well, so I think that one looks pretty good. So now the central maximum is really only that much right there. If I put my finger on it, I think you can see it a little bit better. Okay, it's only that big, whereas previously it was almost the entire size of this, and you can see the fringes going off to the side here on both sides. So that's what a single slit looks like. Now what if we put other things involved? If we put in some other things here. I was going to show you circular apertures. That would be here. Okay. And that one you cannot see very well. And that one, I think also you cannot see very well. All right, maybe if I cover, well, I'm trying to be able to show you that there's light and dark fringes from the circular aperture, just like you'd expect from a slit, but it does not seem to be showing up very well. You can definitely see that's the central max where my thumb was, but you, I don't think, can see the extra rings that go on. All right, so let's skip to a square lattice here. So if I have a square array of points, this is the diffraction pattern I get. And you can see maybe you can see that there's obviously a very central bright right there, but there's very definite brights, and then there's a slight dark right here as I go across, and then some more brights, and then some more brights and darks and brights and darks. So this is a more complicated pattern because this array is a set of points arranged in a in a square lattice, right? I can take one that's that way. This would be hexagonal, right? So I can make different diffraction patterns with these things. That one's just a bunch of dots on the screen, and then this one's a bunch of holes on the screen. But anyways, so different diffraction patterns. This is a field when it's used to find crystal structure. It's known as crystallography. But what I want to do today is show you this. So what do we have there? That's not what I want to show you. What I want to show you is, nope, that's wrong. This way. Okay, is this. Okay, now looking closely at this pattern, it's barely visible, but you can see there is some interference within the central maximum here. I think if you can just see, there's some dark lines in the bright central here. So this is an interference pattern, and the diffraction pattern is the large central maximum and then the subsequent secondary maxima out here. These are the diffraction pattern parts, and the little tiny ones in here, if I put my finger in the way, that works a little better. The little tiny ones, those are interference patterns. Okay, that's the double slit pattern. And the large envelope that we've talked about is the single slit intensity pattern. So now let's go to 3 slits and look at the difference that happens here. Okay, you're not going to be able to see too much of it. Let's try the finger trick again here. Now I'm looking at slightly sharper peaks. The peaks are narrower than they were before, right? If I look out here, I'm seeing narrower peaks from the interference pattern. If I go to 4 slits, okay, now you can look at it again. I'm still getting the same single slit pattern, but look, the maxima are becoming more dot-like. They're becoming more dot-like and very sharper, okay? And we go to 5 slits here, okay? And in between the sharp, bright peaks, I'm not sure if you can see, but there are smaller, less bright secondary maxes. Okay, and those have been slowly getting dimmer and dimmer as I go up in the number of slits. Okay, so now what I'm going to do is I'm going to take that. So that's just more multiple slits. Okay, and now what I'm going to do is let's see if I can just leave that there. I'm going to hold this in the way. Okay, and now you're looking at, this is still the central maximum of the laser beam, but notice over here, okay, I've got nothing until I get that first maximum over there. So as I go up and up and up in slit number, right, then what I'm able to see is that the peaks get sharper and the secondary maxima get dimmer and dimmer. So in between here and here, there's nothing here. Oops, now I'm covering with the laptop, right? So this is the central maximum. This would be the first maximum. The second maximum you can just barely see is over there. That's it right there. That's the second max, right? But this is a way to separate wavelengths from one another, okay? So and I'm not sure if I could actually do this, but if I take the green one and I replace it with, say, a red one, right? Let's turn this off for a sec. Well, actually, I'm going to leave that on so I can line up my maximum here. Where is that one? All right, so there's the central maximum of my red one. And you'll notice where the first maxima is for the red, right, versus where it is for the green, right? Slightly different position, right? So notice that the green is slightly in, the reds are slightly out further, right? So if you just look at my shadow on the wall there, so that's about near where my elbow is. If I try to keep that, you'll notice that's a little bit further in, okay? So that is the diffraction grating. It's very useful for separating wavelengths and finding out what wavelengths are involved in light. Okay, so it's basically what you might think of as being a prism, but it has very definite properties that make the measurement of the wavelengths much easier. All right, so now we're in the dark. I'm going to walk back and turn the lights back on so we can see in here. We'll get started on some analysis. Okay, good. That glare is not so bad anymore. So that is what a diffraction grating is, just so you can take a look at it. This is basically what it looks like. These are the things whereby if you hold them up to your eye and you look around at regular light, you see rainbows. Okay, like I said, it's not exactly, but it has the same effect as a prism. Okay, the glass, as you did in the homework problem with the water, right? The wavelengths, the different colors separate, because the index in glass and water is different for the different frequencies, right? That's not what's happening here. This is just an interference issue. Okay, this is an interference and a path length difference issue for the two or multiple different types of wavelengths. All right, so what we have is just the ability to separate them out based on, well, how many wavelengths are going to fit into your path length difference? And when you want construction, that path length difference has to change so that you can get the one wavelength in. So if I have a bigger wavelength, I need more of an angle. So as you were seeing with the red is slightly further away. The first maximum is slightly further away from the central. And for the green, which has a slightly shorter wavelength, it's a little bit closer. Okay. So we're going to discuss some of the properties of the diffraction grating today. And what we have here is, like I was showing you with the 2, 3, 4, 5 slit setup. It's often easier to think of this as a limiting procedure. Okay, so you're going to take 6 and then 10 and then 20 sources and things like that. And you're going to think about it. When you get to a diffraction grating like this one, I'll tell you it has 15,000 slits per inch is what it says on it. So that's a lot closer than our typical double slit experiments have been. The ones at least we've been talking about where you say you have, I got like a 1/4 of a millimeter or a 1/2 millimeter between slits. There's 15,000 in an inch. So there's like 7,000 in 2 centimeters, 35. So you're talking about things that are in the hundredths and the thousandths of a millimeter sometimes rather than the 10th. Okay. So let's take a look at diffraction gratings. And the idea is, this is many slits, very closely spaced together. In fact, there are also, relatively speaking, there are 2 types. The one that I showed you here is one in which light passes through. It's called a transmission grating. And of course, you also can have the reflection grating. And that would be more like the underside of a DVD. one of those discs, right? That almost nobody ever uses anymore. CDs, DVDs, they have grooves, just like an old vinyl record, but they're really close together. And they're so close that you can get you can look at them and see the rainbows. It's because it's a reflection diffraction grating. So the idea here is that ultimately, when you're looking at many slits closely spaced, you're looking at many sources closely spaced, and so it's essentially the same idea as the single slit. In other words, the diffraction is happening because we're thinking of many, many, many waves going. And actually, I just wanted to say something here because I've gotten a lot of questions about this. What's the difference between diffraction and interference? There is no real difference except for the number of waves that you're thinking about. The behavior is exactly the same. Interference, when we were looking at the double slit interference, we were looking at only the behavior of 2 waves, okay? When we were looking at the single slit, it becomes the behavior of an infinity of waves, okay? Or if you use a reasonable limiting procedure, it's 8 to 10 to 12 to 14 waves, right? But the point is it's more than 2, and the same idea is happening here. It's still the same interference idea of the waves meeting, going like this or going like this. It's just that how many are you dealing with, okay? So many slits closely spaced is kind of the same thing as many sources closely spaced. So you can draw them in like this and say, oh, well, I have waves coming off in different directions, right? I can look at what happens if I go off at this angle like this, right? Now, if these are coherent, then of course, going straight through is exactly the same as it has been with the single slit and the double slit. That's where you get your central maximum. And you saw that with the diffraction grating. The laser still shines straight through it and constructively interferes there. Now, what happens if I go off to an angle? Well, what happens if I go off to an angle, and this of course is our angle theta, that we want to think about path length difference between the sources. Now, for most angles in the diffraction grating, we got cancellation, okay? And so it goes back to the same kind of idea as it was before, in the sense that if I look at the path length difference between neighboring sources and neighboring waves, then I look at this path length difference and I say, all right, well, if I just draw straight up, this right here is my path length difference. And if that's a half a wavelength, then these two are canceling, which means that these two are canceling and these two are canceling and these two are canceling, and therefore I get complete destructive interference. Okay, great. Well, you can also make the same argument if I said, well, what if we looked at a slightly greater angle and it was in fact these two that canceled with each other? Now that's a half a wavelength out. It's numbers 1 and 3. Well, now those two will cancel and these two will cancel and those two. So I just skip every one and I still pairwise cancel. Okay. So this is why for most of the pattern, you get destruction, because there's so many sources that it doesn't take very much, right? You go straight and everybody's happy and everybody constructively interferes because they're all in the same swimming in phase. Now I go slightly off to the side, and that means this one is lambda over 2 out of phase with that one, which means the next one is lambda over 2 out of phase with that one over there, and then one over there, and that one. So it destroys. So then I go to a slightly bigger angle, right? And okay, instead of going all the way over there for the path length difference, I only have to go to this one. But these two still cancel. And that means those two cancel, and that means those two cancel, and those two cancel. And then I go to a bigger angle, and I say, okay, well now the path length difference is one line where it's just this one I'm canceling with, my exact neighbor, and I go to the next ones, right? So it's always pairwise canceling. It just depends which other source are you picking, because there are thousands of them, right? So there's many opportunities for cancellation here. If you get lucky and you say, aha, I'm only one wavelength out of phase, right, with that one over there, my neighbor, right? I got a 1 wavelength in my path length difference. So this gives you the idea that it's mostly destructive. mostly destructive. Because I have so many sources that I can always pick one that's about half a wavelength out of phase with me, and we'll destroy each other. And that means my neighbors on either side would destroy with that one's neighbors on either side, and then their neighbors destroy with their neighbor, etc., right? It's mostly destructive due to the number of sources. So it still works just like it did with the single slit as pairwise cancellation. Okay. So when you get finally to constructive interference, then what you find is that the wavelength the path length difference between successive ones is a wavelength. All right, so we have all right, if we have one, the path length difference is now one wavelength. So here I have a path length difference, and here I have a path length difference, and maybe that's now 2 wavelengths between those ones, and it's 3 between these ones. Right, etc., etc. And I can go and say, oh, they're all exactly a wavelength out from each other. Right? So say I have one wavelength right there. One wavelength in that one path length difference. 2 wavelengths in this path length difference between the first one and the third one. 2 lambda there. 1 lambda there. 3 lambda in this one. So each neighboring set is a wavelength away from the previous one. Right? That means that at that angle, I'm going to be able to say that's constructive interference with this one, and then this one's constructive interference with this one, and this one's constructively interfering with this one, and this one, and this one, and this one. And once they all kind of click into place like that, that's when you get your bright spot. Okay? But notice that this is the exact same condition that we had for the double slit interference. I had 2 waves coming in. Right? I had this set of waves coming in, and I said, okay, if I incline and I look over at that angle, then the difference in the path, right, which is the amount this one travels, that's a little bit extra, if there's 1 wavelength in that path length difference, I have construction. If I have 2, then I have construction. If I have 3, I have construction. Okay? And that's what's happening here. So therefore, the condition is essentially the exact same condition. This means that we get constructive interference, which is a bright spot. And that's equal to a bright spot. Now note that this bright spot, as you saw with the diffraction grating, right? This bright spot is pretty far away from the central maximum. The central maximum for the green one was here, and then the first maximum was over there. So that's destruction all the way from here all the way out to here, until finally, they all got in the line and they clicked in, and all of a sudden the planets all lined up and everybody was going, oh yeah, this is it, construction right here. And then you go a little bit further away and it's total chaos again, right? Everybody's destroying everybody else. So, the other thing that happens for that is you can see that we're no longer at a small angle, okay? There's no longer a small angle situation here, all right? The constructive interference bright spot, it's the same condition as with the double slit. Therefore, the constructive interference is the same condition as it was with the double slit. All right, so this is construction happens when d sine theta is equal to m lambda. That's your constructive interference for the diffraction grating. Now, you're going to have to remember to keep these things straight in your mind. And what I have tried to give you, since we're going into the celebration next week, are ways to quickly and hopefully easily just derive these things. I highly encourage that you don't rely on memorizing, that you do rely on drawing a quick picture and going, oh yeah, I've got 1.5 wavelengths in the path length difference. Oh, this is destructive. right? And understanding what that means, okay? How does path length difference, or how does phase, or how whatever relate to the interference of the waves, okay? So I highly encourage that you think about the physics behind this and how to represent these constructive and destructive interferences in terms of the wavelength phases and their causes, rather than just memorizing a bunch of equations, okay? Now, that may be an easy thing to do because you can memorize equations and spit them all back out. That's great. But we want to know what is the physics behind a lot of this, okay? So this is the construction. We do not have a destructive interference condition for the diffraction grating because essentially it's always destructive except for when this happens. And this is really rare, as you saw, in a sense of how much destruction happens prior to getting to a bright spot. There you go. All right. Next bright fringe is further away. Lots of destruction in between that. There's no point in talking about destruction because it's basically always happening. Okay. Okay. So this is the situation with the diffraction grating. I thought we could do a quick example here. And one of the points of this example is going to be, let's talk about what all these things mean. Okay. Now, number one, I've already mentioned the small angle approximation is no longer valid here. So sine theta being tangent theta, y over d, that has to be off the table here because the angle is just too big. Okay. To the first maximum, right? You saw I had to bring the computer all the way in. And when we were here talking about the double slit, the first maximum was, right, you were talking about something that was here and then something that was right next to it. Okay. And what would be interesting is to see if we can do some resolution on that thing. I don't know if you can tell, that's two dots right there. But anyways, for the diffraction grating, you're talking about a dot here and then a dot over there. Okay, so this is not a small angle. Just be aware of that. No small angle. Okay, no small angles. And also then what is the quantity little d? Okay, little d here, in the double slit, it was the distance between slits. Well, it's the same thing here. But notice that we have so many slits. Hopefully it's a fairly consistent spacing, but basically, right, it's that distance right there. That's distance d from one slit or source, as I did it here, to the next. Now, that's a little different because in something like this, it's not going to tell you what this number is. We're going to have to figure that out. What it will tell you is that there are 15,000 slits per inch, or what they normally refer to are lines. Lines meaning like they made scratches in something. So 15,000 lines per inch. From that, we can get what little d is, okay? It's pretty straightforward, but just be aware that that's not something that's just straight given. You have to figure this out first, okay? So that's the d. No theta, no small angle on the theta, and then m lambda is basically the same as it was before with the double slit in terms of fringe number, 0 for the central maximum, because we are talking about path length differences here. And then for a diffraction grating, you're typically going to be operating with either first order or second order. It's pretty unlikely to get past that because it's a diffraction sense, so the intensity is dropping. All right, and wavelength is still wavelength. All right, so let's do an example involving some of this stuff, and then we'll go back in and talk about some of the cool properties of the diffraction grating. All right, so let's set up an example here. Where I have a diffraction grating, and let's suppose that I have 25,000 lines per centimeter. Okay, now I'm going to shine light of two different wavelengths into the diffraction grating. I'm going to ask, what's their angular separations? Okay. Light of, first say lambda 1 here is 400 nanometers. And then after that, lambda 2, I'm going to change to 500 nanometers. Illuminates the grating. And then what I want to ask is, how far angularly are the first maxima? So that'll be my first question. What is the difference in the angle? Say the angular separation of the first maxima. All right, so we'll start with that. Well, this does not seem to be erasing very well today. Yeah, you can still see that, huh? Oh well. Good stuff. All right, so first thing is, let's tackle what's going on here with the grating. So I've got a number of lines, or a number of slits, or however you like to think of it, or if you like, a number of sources. Okay, let's suppose I've got a central bright fringe here. And then I'm going to have my first bright spot, the first max over here. And then I have another one on that side, but I'll just draw it down here. Now, first question is, with the wavelength being 400 nanometers, this bright spot's going to be at a certain place on the screen. Okay, great. What do I expect to happen to this maximum if I change the wavelength to 500 nanometers? Now, we've just seen what happens when you increase the wavelength. We've just seen what happens to the pattern through the diffraction grating as you increase the wavelength. But I would like to encourage thinking of stuff like that prior, because, you know, in a couple of days you may have forgotten something like this. So thinking about, all right, so what happens if I increase the wavelength? What's going to happen to the distance of the first maximum, like the angular distance of the first maximum here to here, right? That's the theta. It's not small, not a small angle anymore. If I increase the wavelength, then I expect to see that that fringe gets pushed further away. Why do I expect to see that? Well, we've also talked about this, and that's because if I'm looking at the path length difference, which is the fundamental quantity causing interference here, then when I want all of those little sources to be one wavelength out, I have to pick an angle such that the path length difference between neighboring sources is large enough to fit a wavelength into. So if I take this and this, and I say, look, my path length difference is, well, this is going to be too small for you to probably see, so let me make this bigger. If I take this one here and then this one here, okay, and I look at the path length difference between these, right, that's it right there. That's the path length difference. Now, if I'm going to say, well, I've got the ability to put one wavelength in there, okay, and it's going to fit just perfectly. So therefore, it's going to constructively interfere with this one. Okay, Now I'm going to lengthen the wavelength. So now my wavelength doesn't look like this, doesn't fit in here. What happens now if my wavelength looks like this? But I still want construction. What I have to do is increase this distance. How do I do that? I go further on an angle like that, right? I go out here to where they're like this. And I look at the path length difference. And I go, oh yeah, look at this thing now. It's gonna fit. Okay, so that's a much greater angle. That's how you increase the path length difference and therefore understand physically why these wavelengths are going to occur, or these wavelengths are going to produce maxima at different angles. Nonetheless, if I go from 400 to 500, I would suppose that this could be my 400, this could be my lambda 1 maximum, and then my lambda 2 maximum might be over here somewhere. So that would be theta 1. Here's first maximum for lambda 2. And then this value here, theta 2. So what I'm looking for is the angular separation. That is essentially theta 2 minus theta 1. All right, we have the ability to solve for the thetas as long as we know what the distance little d is. Well, notice we don't know the distance little d, but we do have the ability to figure it out. So with 25,000 lines per centimeter, that means, remember now, little d is a distance between slits. So that means in one centimeter, there are 25,000 slits, and therefore little d is just 1 over, right? Is 1 over that number with the appropriate units. Okay, so if I divide these numbers, I'm going to get some number that's going to be pretty small, some 10 to the minus 4th in centimeters. Okay, and then I can take that and use it here, because ultimately to find these angles, how do I do that? Well, I'm going to take theta 2 and I'm going to say, well, I know that the sine of theta 2 is equal to, because I'm looking at interference maximum number 1, it's just lambda divided by d. And then all I have to do is arc sine both sides, and I'm going to get the angle for these. Okay, so for lambda 2, theta 2 is lambda 2, and lambda 2 is 500. So this would be 500 nanometers divided by, and d is 1 over 25,000 centimeters. 1 centimeter divided by 25,000. So I'm going to have to, first of all, deal with these units. Okay, I know I'm going to have a factor of 10 to the 7 in here somewhere, and I'm going to have to make these units copacetic, because I need those length units to go away with each other. All right. So that means I can do either both things in nanometers or both things in centimeters. Let's go ahead and do them both in centimeters. I guess that would be easier. This is 25,000 divided by 1 centimeter, multiplying 500 nanometers. That's 10 to the minus 9th of a meter, so this is 10 to the minus 7th of a centimeter. And now I'm going to delete these centimeters from the whole shebang here, and I'm going to get, let's see, I'm going to 10 to the minus 7, so we'll go 6, 5, 4, 3, 2. And I got 5 times 25, so then I'm down to 2 here. And 5 times 25 is going to be 125, which is going to take care of the other 2. Right, so I'm going to end up with 25 times 5 is 125 times 10 to the minus 2, which would give me 0.125. Or no, sorry, 1.25. 1.25. 1.25. seem very good at all, does it? So I messed something up here. I wonder what it was. Oh. Can't have that. Oh well. Get some calculation here that you mess up, and you figure out what happened. D is 1 over 25,000. That's 5. Oh yeah, no, that's right. That's right. 500 nanometers. 500 nanometers times 10 to the minus 9 meters. Huh. Oh well, I don't see it right away. What did I get wrong here? 7, 6, 5, 4, 3, 2. I've got 1, 2.25. Huh. Well, I don't see it. If you see it, let me know. Let's see here. Just take a look. Yeah, I don't see it right now. I must have got something wrong in how I multiplied these numbers out here. 10 to the minus 7 or 10 to the minus 6. Well, sorry, I don't know. Anyway, you'd be able to figure that number out. Let's make a guess here. Let's suppose it's like, let's make a guess here. Let's suppose it's like 5 degrees. When I take the angle, suppose I get a number like 5 degrees from it. And then I'm going to take the same exact thing here with sine of theta 1. I'm going to do the same calculation with sine of theta 1, and that's going to be lambda, I put lambda 2 here, lambda 1 over d. And I'm going to do the same calculation, although maybe hopefully we'll do it right next time. No, I don't know. Probably not. And so I'm going to be able to take a difference between these two, all right? So theta 1 here, maybe theta 1 turns out to be 4.8 degrees or 4.5 degrees or something like that, or 4.2 degrees, whatever. So that my total delta theta is then 0.8 degrees between the two peaks. So what that means is if I look at it from a situation of how far away on a screen would I be interested in seeing these peaks, right? If I put my screen maybe 2 meters away, I could determine what is the delta in y from this, okay? So that measured to here as y1, and then that measured to here as y2. Notice, however, that we're still not using the small angle approximation. I'm not going to do y over d for my angle. I do have to go in and actually calculate out all the sines and then arc sine everything and find the angles, and then go back in and do the proper tangents to find the y's over d's and stuff like that. So you do have to use the full trig function with this analysis because the maxima are not small distances away. All right. Okay, so that's the first question. What's the angular separation? Well, it's something, and apparently I was not quite figuring out what's going on. Some type of calculator mistake. If I look at my second part to this question, let's look at the second part to this question, which is at what angle and at what fringe number are these two going to overlap? Okay. Where do they overlap? Okay, so what I would be doing is shining them both through at the same time and looking on the screen. Oh, I've got a 1 and a 2 here. I'm sorry, a 1 and a 2. Lambda 1 and lambda 2 here is their first maximum. Lambda 1 and lambda 2 over there is their second maximum. Lambda 3 and lambda 4 over there is their third maximum, right? Etc. etc. Lambda 4 and lambda 5, etc. etc. So the question is, where do the fringes overlap? Well, if you look at what you're effectively doing here is you're looking at which angle, right? I'm looking for an angle at which lambda 1, a lambda 1 fringe is directly on top of a lambda 2 fringe. Now, they can't possibly be the same fringe number, okay? Because we know there's going to be an angular separation between all the fringes no matter what. So what I want to do is say, well, these signs are the same. The signs of the angles are the same. Sine theta 1 equals sine theta 2. That's what overlap means, okay? But now notice then that I can say for this one then that M1 is for the lambda 1. M1 times lambda 1 over little d should equal M2 times lambda 2 over little d. And thankfully we can get rid of our pesky little d because that's the same for both. But notice that the M1 and the M2 are different fringe numbers for the different wavelengths, because we already know that if they're both 4, well then these are not going to be overlapping, okay? What I'm going to find here is that I want basically M1, we'll do M1 over M2. M1 over M2, right? If I take that and under here, then I'm going to take that and put it under there. This is lambda 2 over lambda 1, right? Which is, in this case, 500 over 400. Now, if I just look at, sorry. Okay, computer fun. All right, if I just look at the ratio of these things, right? Reduce it to the lowest possible thing. I'm just going to get 5 and 4. Such that if I take M1, which is the fringe number of the smaller wavelength, and I say I've had more fringes of the smaller wavelength and fewer fringes of the longer wavelength, right? So at number 5 for the 400, at number 4 for the 500, these two will overlap. They'll be right on top of each other. But I will have more fringes for the lower wavelength than I do in front of that than I do the other one. Okay. Question being now, where do they overlap? Well, I know the order number that they overlap. So what's the point on the screen at which they would overlap? I can take either one of these fringe numbers and calculate what is the actual angle that I set equal to each other here, right? By saying now, okay, what I'm going to do is look at sine of theta being equal to 5 lambda 1 divided by little d. And since apparently I failed at calculating these angles, I'll just leave that to you to do that. But you'll come out with an angle that should be exactly reproduced were I to have put 4 lambda 2 here, right? And you can see it would, because 5 of those and 4 of those is going to be the exact ratio that you want, okay? So that's the point on the screen where they overlap. Then the other question is, what's the total number of fringes that I'm going to see, right? Well, no, I should step back from that. What's the total number of fringes that could appear on the screen? Let me put it that way. Maybe not that we're seeing, but what's the largest fringe number that could appear? All right. So in that case, you'd say, what is the largest fringe number to appear? All right. What's the largest fringe number? Well, in this case, I'm trying to figure out what's the grand total number of fringe orders that I could possibly have. So in some sense, I'm solving for little m here. Okay, but I want to make it the biggest possible thing it could be. And if I look at my constructive maxima, right, it's going to be related to what's the biggest possible value that sine theta can take. well, I can't have sine of theta be more than 1. Well, maybe I can if I do a calculation like this. That means my theta can't be more than 90 degrees. And physically, that can't happen anyways because my set of slits or sources or whatever these things are, right? I can't have them going, right? If they were going more than 90 degrees, it'd be going backwards somehow, okay? So here, I'm going to say M, the maximum, is equal to sine of theta, which is going to be 1, and this is now going to be d over lambda. So if I want to find how many of lambda 1s appear on here, I'll use lambda 1 in here. Or if I use 2, then I can use the lambda 2s, and that'll be a different number, okay? In this case, it'd be 1 over 25,000 of the centimeter variety divided by 400 of the nanometer variety. Oops, centimeters. Like so. And you're going to get a straight number, okay? And that number is going to be the maximum order that you're going to get on the screen. All right, so this is set when theta be 90 degrees. Right? In other words, there's no possibility that I could look past that. That's the biggest it could get. All right, so that's essentially how the diffraction grating is dealt with in the straightforward sense. Okay, remember no small angles, and you have to calculate what your little d is. Let's look at some of the behaviors now of the diffraction grating such that it helps us to resolve wavelengths from one another. So if I have two wavelengths that are very closely spaced, then I want to be able to see how can I distinguish between them on the screen, okay? And this is a typical situation for people like astronomers who rely on the light to tell us what's happening, right? Astronomers are going to say, well, I'm looking at the light from the star and I'm, excuse me, and I'm interested in what kind of wavelengths it has in it, okay? So then you're going to say, I'm going to put that light through a diffraction grating and I'm going to try to separate out the wavelength and look for particular light that shows that there's a particular element in here, okay? So when we look at the light, it's telling us about the chemical composition. And that's the cool part. And we have basically two quantities that help us with resolving very closely spaced wavelengths. All right. And the quantities are the dispersion which basically tells you the angular separations of different wavelengths. And we also have something called the resolution, which is the ability of the thing to distinguish between the two. Okay, so I would say that this has to do with like angular separation. Okay, in the same sense that that's what we were just doing with the with this example here. And the resolution is the sharpness of the peaks. So how fine is that peak of the maximum? Is it kind of spread out a lot? Does it have a lot of slop in it? Is it really well defined, like the peak is right there, it's a line almost? right? And you're going to say, oh, that's really quite right there, and then I've got a wavelength right next to it, type of thing, okay? So these two quantities essentially depend on some of the attributes of the diffraction grating itself, okay? So let's take a look at the dispersion. Dispersion is asking how does the wavelength, how does the angle vary with different wavelengths? Okay, so the dispersion is essentially asking the question, what is the quantity d theta d lambda? Right? How does the angle change with wavelength? So can we put different wavelengths through and get them pushed away from each other, right? How does angle change with wavelength? So if we wanted to calculate how to find the dispersion, we could do that because we have, I'm sadly going to find that the differential operator and our slit spacing are using the same variable here. So for this purpose, I'm going to change the slit variable into something else instead of little d. Maybe we can change it into something like S or something, all right? So that instead of writing d sine theta, I'm going to write S sine theta equals m lambda instead of d, so that we can hit this with a differential operator. I'm going to do this, and I'm going to just hit both sides of this thing with the differential operator. Now, things that are changing, we want to know relationships between the angle and the wavelength, okay? The grating separation itself is not going to be changing, so this will be a constant. It will flip out past the differential operator. And I'm going to pick a particular order number so that we don't have to worry about the m also changing, and that way we can isolate just the theta and how it changes with lambda. All right, so if I use the chain rule to get through all of this stuff, what I'm going to find is the s flips out because it's constant. The d is going to operate on the sine theta, but I know how to take the derivative of a sine theta. That just gives me the cosine theta. Right? That's going to give me cos theta d theta. And go over to the other side, the m is going to flip out as well. It's going to pop away here, and then I'm going to get the differential operator on the lambda, but it's by itself, so this just becomes d lambda. We can now actually form up this d theta d lambda. If I swing this underneath here, and I push all that stuff underneath there, I can come up with what the d theta d lambda looks like. It depends on the order number here, and then I'm going to push all this stuff underneath here and say it's s cos theta, where s is little d. So if we looked back at the previous problem here with these two wavelengths, can I use this to get to that answer? Yeah, I can now. Instead of going through and mechanically calculating, I got to take the arc sine of this one and then the arc sine of this one, then I got to difference those two angles. If I just pick my order number, maybe it's 1 or 2 or whatever, I'm interested in the angular separation between the fringes, right? It's going to be, this is, remember, our little d. So maybe I can I change it back at this point? Is it d cos theta? Maybe. We'll do it. I'll change it back to d for this one now, okay? So see, if you skipped ahead in the video, see you didn't see that happening, and you're wondering how is s related to d, and how did this all happen? Well, don't skip ahead in the video. Watch it on double speed, of course, but don't skip ahead. D cos theta, so we're going to look at the angle at which the maximum is appearing and looking at how the angle is changing with the wavelengths. Now I've changed the wavelength and I'm going to get a different angle, and this kind of tells us how it's going to happen. I see that we're just about running out of time here, so I'm just going to quickly talk about the resolution. The resolution is fairly, it's basically exactly what you think it would be. It's the sharpness of the peak. In other words, how much resolution, how much, I can't use the same term to define the term. So how much play is there in the wavelength around one of its maxima? Okay, so if I'm looking at a peak for say 500 nanometers, okay, well, how big is that peak? Does it go from 450 to 550? Right, that's a pretty poor resolution. Does it go from 495 to 505? That's a bit of a better resolution. Okay, so this gives you the ability to find how large the peaks are. And if you do a little bit of fooling around, you'll find out that it reduces to a fairly straightforward thing, which is just n times m, where m is the order number, right? It's still the same thing as m, but and n is the total number of slits in the array. All right. So with that all being said, I think that basically covers what we need to know for diffraction gratings. Should we find anything else to do, well, we can do that tomorrow and just finish up what we need to. Diffraction gratings, so yeah, go ahead and assume that that's going to be on the celebration as well. And you should have enough now to go through and do the rest of your homework problems. Alrighty, so tomorrow we'll look and see what we can find out about any gaps that we need to fill in, or anything that needs to happen there, and we'll go around from there. So I will say happy day to the rest of you, and see you next time.